Okay, so our second talk is about exactly once. So if you know about exactly once, it is actually a feature that has been developed and contributed into Apache Kafka since 2011, which is like 2 years ago. 2 years in open source software development is actually a pretty long time, because imagine right now we have Kafka 2.3 release already, and exactly once is introduced in 2011, right? But it's never like a done deal from engineering point of view. Since its introduction, more and more people, especially the users of Kafka Streams and Kafka Connect, is actually enabling exactly once. And the community has actually been trying to investigate into different issues after we have first introduced the version. And we want to actually improve on, especially on the performance, on the scalability of enabling exactly once. So in the second talk, we will have Jason and Boyang talking about what are the lessons learned from developing the exactly once features, and what are the ongoing works that we actually are working on with the community. And we hope to actually get those improvements into the next release of Apache Kafka. So with no further delay, we have Jason and Boyang. Thank you.
Thanks, Boja. Okay, so this is just an overview of our talk. So basically what we're going to do is we're going to talk about what actually is exactly once, what does it mean, how does it work under the covers, and then we're going to go through some of the problems that we've had and how we're going to go, how we're planning to fix them. So I'm going to cover the first half of it, kind of identify, explain how it works and all this, and then Boyang is going to jump in and explain some of the work since he's actually doing it. So first off, I just want to give kind of some background about exactly once semantics. What problem is it solving really, and what guarantees is it actually designed to give? The scenario is really that you've got, you want to really be thinking about like Kafka Streams, for example, where you have some kind of input topic and an output topic. You're reading from the input, you're doing some kind of processing, and then you're writing the output. So the guarantee that exactly once semantics is trying to give you is that each input that you have is reflected in the output exactly once. So for example, we read this record A, we do some processing, and out pops out A prime. And so on. We continue in this way. We don't get any duplicates. So the Kafka will handle the duplication, handle any kind of failures that come up, and then we'll write the data exactly once. So I gave an example basically where it's like just one-to-one input to output. It doesn't have to be that way. So for example, if we have the log containing some kind of counts, like in this case, just each record just has one, and the purpose of our processor is to just sum up all those values. It doesn't have to be a one-to-one mapping from the input to the output. So for example, we might read the first two values, sum those up, write out the summation, and then similarly continue in this process. So there's no actual requirement about one-to-one. It's really more about guaranteeing that each input is reflected exactly once in the output. Okay. And similarly, in the initial example, and most of the examples here, we have just one input topic and one output topic. That also doesn't have to be the case. So you can have multiple output topics, multiple output partitions, and we're just looking for a similar guarantee. So A and B are processed, and the values are reflected in the output, and so on. Just for simplicity in all of these examples, I'm just going to show an input and output topic because that's enough to show most of the interesting cases that we want to talk about. And if we want to start being a little bit more precise about what exactly once is doing, so even with a single input output partition, there's actually this other output partition which is implicit in the way that the consumer works. So when the consumer is reading its data, it is always keeping track of its position in the input partitions. So the input, this position basically is written to another topic. So the guarantee that exactly once gives you is really about ensuring the atomicity of those two writes at the same time. So when the data is reflected in the output, so is the position. So basically, even like with a single input and output partition, there's another output partition that we're concerned about, which is the position. So if we want to like start looking at this process in a little bit more detail, what it really consists of is not read, process, write, but first we read the position from this position topic. We do the reading, process it, write it, and then we're writing the output, both the output and the position, and so on. Okay, so, and what we're looking for is basically that all of this is atomic. So it either all succeeds, the full pipeline succeeds, or none of it does. Okay, so the way this works in Kafka is we basically have two parts to guarantee this atomicity. So number one is we have a transactional write across multiple partitions. So that solves the part about how do we ensure that the position and the output are written to the log in a a transactional way. And then the second part is more subtle, and which takes a little bit more explanation, is basically a protocol to guarantee a single writer. And I'll explain in a little bit more detail what that means. So first let me just briefly talk about the transactional. Surprisingly, this is actually the part that's easiest to explain. So because it's a fairly standard two-phase commit protocol. So what we're focused on in this protocol is really the last two parts, the writing of the offset and the writing of the data. So in Kafka, we have this protocol where we start with a begin. I think I got some examples to go through this in a little bit more detail. So let me describe what's on the screen. So we've got the input partition as we have before, and then we've got that two output partitions, the position where we're storing our consumer offsets, and then where we're storing the data. In addition to that, we have a transaction log. The transaction log is what we're using to implement the two-phase commit. So the basic way this works is we'll read some input. We'll add that, before we do any writes to any of the partitions, we'll write a message to the transaction log saying we're going to write. Basically, we're going to start this transaction, and it's going to include this output partition O. Okay, then we can go ahead and do the write. Now, I've grayed this out here because at this point, the data is in the log, but it hasn't been committed yet. Its fate is still uncertain at this point. So it's not visible to consumers, and basically another step has to be taken before it becomes visible. So the second thing is, when we wrote to the output partition, we also need to write to the consumer offsets to say, okay, we read from this position, and now we're going to commit that position. So the position is, the consumer offsets is just another topic. It's just a partition. So it's not really distinguished from the transactional perspective. So what we do is we write a message to the transaction log saying, okay, now I'm going to write something to the consumer offsets. So once we have that record committed, then we can go ahead and commit our position. And then once we've finished all of this, then finally we go ahead and we commit the transaction. So this is the two-phase part. So it consists first of a message to the transaction log saying, okay, we're preparing to commit. And basically this means that at this point, like you can't go back. This is like the point of no return. So once you write that record, it's doomed to roll forward, is what we say. But it hasn't happened yet, so the data is not visible yet. So then the second parts of it are we write actually a marker into the transaction log saying, or sorry, into the output topics saying, okay, this now is committed. And at that point, that's when it becomes visible. So we do the same thing. Then once all the markers have been written to those output topics, then we write another message to the transaction log saying, basically, we finished this transaction, and we'll reset our state. Okay, and then just the other case that we want to explain is, yeah, so you basically, all of this stuff, can happen as before. We started a transaction. We wrote some records to transaction log saying, okay, these partitions are included in the transaction. Now, what happens is maybe we could crash. So if our process crashes, then we have basically a transaction coordinator, which is responsible for detecting that the crash has happened. And at this point, we abort the transaction. So we go through a similar two-phase process. We say we're preparing to abort. This is the point of no return. And then we abort that data. And then the consumer basically will not see that data. They will skip over it. And similarly, we finish it. Okay, so now I want to talk about the thing that's a little bit more difficult to explain, which is this protocol to guarantee a single writer. And we have this notion in, yeah, I'll get to it. So what I've been describing right now, this, we have this input topic, we do some processing, and we have an output topic. So in practice, you actually have multiple processors which are, cooperating in order to consume from a number of input partitions. So, and similarly, you have a number of output partitions that you're trying to write to. So, what we say about the single writer, it doesn't mean that there's only one writer for each output partition. It's more about actually the input partition. What we're looking for is a guarantee that for each input partition, there's only a single writer which is responsible for reading that data and writing the output. So the real guarantee is really about the input. Okay, so I've demonstrated it, or just shown it up here. Each color is kind of representing a different scope, a different single writer scope. And basically when we have, in Kafka, of course, what we're talking about really is some kind of a consumer group where the partitions that we're consuming are divided among the members of the group. And then so whenever you have some kind of failure, then that partition is reassigned to another member. So basically like its single writer scope can follow along with it. Okay, so in order to make this work, there's basically two problems that we have to solve. So the first problem is what we call the initialization problem. The initialization problem is about how we do this handoff. So when we had a failure, let me just get to the example. So let's say that processor 1 at this moment has been assigned a partition and it's doing a transactional processing loop just like we described before. So we're reading the inputs, we're writing the outputs, and then we're trying to commit the data. Now, the transaction can be in any state that we saw it in those previous slides. So it can be that we haven't decided basically whether it's going to be aborted or committed. It could be that we've already decided, like we've written that prepare marker, but we haven't finished the rest. It could also be the case that we actually completed it. So all of those things are possible, and they all have to be handled. So suppose that we were in the process of committing the transaction. So it could be like we wrote the prepare marker to the transaction log, but the output, we haven't committed the data. The markers haven't been written to the output, so they're not visible yet. So basically the risk is now processor 2 gets assigned this input partition, and it wants to pick up where processor 1 had left off. But in order to do so, it has to take into account the fact that we had this ongoing transaction, and which could be committing, aborting, or anything. So the danger is basically that if we don't do that, then we read stale data, and then our guarantees become violated. Okay, so that's basically what I call the initialization problem. It's basically a way that the processor, after it's been assigned a partition, it can resume from a consistent state. The second problem is the fencing problem. So the basic issue that this is trying to address is now processor 1, it may have like a clean failure. It may have actually, someone went and kill-knied the process, it's gone, it's never coming back. But it could also be the case that it had some kind of network blip where it temporarily partitioned from everyone else. It could be in the middle of a long GC. Any of those things are possible. The point is that it could come back at some point. So if we do any kind of handoff, like this becomes a zombie, now we want to transfer the partition over to the other processor, and we're in the middle of this committing state. It's not enough really to make sure that we've recovered from a consistent position. We also have to make sure that I think didn't show very well, but basically we also have to be sure that processor 1 is prevented from interfering with what we're trying to do. So it gets fenced. Basically, as soon as we've taken over, it shouldn't be allowed to make progress anymore. Yeah, so that's what I kind of tried to show there. So those two problems kind of bring us to this notion of what we call in Kafka the transactional ID. So this is configured in the producer. It's a user-defined configuration, and basically its purpose is to define what that single writer scope is. So within the context of a transactional ID, we guarantee that there can only be a single writer. And the way this is enforced, the way we do the fencing, and like distributed systems are, want to do, we add an epoch. So the epoch on every kind of transition is bumped. So if you try to write with an old epoch, then basically you're fenced at that point. And then we have an initialization protocol which guarantees that when we are starting up, like we've just been assigned a partition, that we're able to start from a consistent point. So this is kind of what the initialization protocol looks like. We start off, we bump the epoch. Then we're going through this process. We check, is there a transaction in progress? If it's in progress and it's completing, like we've already written that prepare commit or prepare more abort message, then basically we're going to go through this awaiting completion. If the transaction was in progress but it hasn't been decided yet, then we go ahead and abort it right then. And in the end, after all this is done, we return the new epoch. So the guarantee that we're giving is that by the time this protocol has run, the producer has a new epoch, and it's guaranteed that any previous epoch to that has completed. If they had a transaction ongoing, they won't be able, it's either been completed or they're going to be fenced off. So they can't do anything else, and we're in a clean slate. It doesn't guarantee that a new producer won't be started after us, but that the protocol will guarantee that producer. So the way this works, in this case, I've got 3 input partitions, 3 transactional IDs. When the consumer group, when we have some kind of failure, basically the transactional ID goes along with the consumer. We bump the epoch, and now we're protected. Okay, so yeah, so summarizing, basically this is what we do in Kafka: transactional writes across multiple partitions, and then a protocol for guaranteeing single writer. Okay, and then just to summarize, like basically the way this is working, we bump the transactional ID at the beginning of this process, and then we have the transactional write. So what does this look like in the code? I'm just going to go through this pretty quickly. Basically, we have this API, this init transactions API. If you've seen this before and wonder what it is, well, that initialization protocol that I just described, this is what it's for. So by the time that init transactions returns, we've gone through this protocol, we've guaranteed that we've got a bumped epoch, and now we're in a consistent position, and it's like safe to read from the offsets that we want to start consuming. And then, so basically this, you're pulling from the consumer, starting transaction through the producer. And interesting thing, of course, is that since the consumer offsets are part of the transaction, we don't commit them through the consumer, we commit them through the producer so that they have the transactional state. And finally, we commit the transaction. Okay, so now we're going to start talking about, for the most part, I think it's been a good approach and it's worked well. However, there have been some shortcomings that Guozhang alluded to. So let me cover the first one of those, and then I'll have Boyoung jump in here and talk about the other one. So the first one I think is error resiliency. So probably if anyone has used EOS, you might have encountered this unknown producer ID exception. What does that mean exactly? Let me just kind of briefly describe that. So if we're looking at the Kafka producer and kind of like the architecture of it, what are the different components in it? We have this transaction manager, which is responsible for like managing all of the transaction state. So transaction state for the producer means A few things. So number one, it means like we have a state machine for the transaction. Like we started a transaction, now we're ready to commit it, and so on. Additionally, we have some bookkeeping for every partition that we write to, basically to track where, like sequence numbers for deduplication. So as we're writing things, our requests may fail. We rewrite using same sequence numbers, and the broker is able to deduplicate. So now the problem, if you're looking at it on the broker side now, the broker is also doing some bookkeeping. So the client has these sequence numbers that it's trying to use in order to write to topics. Similarly, the broker is maintaining also a similar set of sequence numbers for producers that it's using in order to deduplicate requests. So if you look inside the broker, what you see is we have some kind of a cache. The cache has, for each producer ID, what's like the epoch and the sequence number. The epoch we already talked about for fencing. The sequence number is used for the purpose of deduplication. So as data is getting written to the log, we're bumping these sequence numbers and so on. So of course in Kafka we have usually finite retention other than compacted topics. And at some point we want to remove the tail of the log. Now when we do so, we may remove some of the state that we had for some of these producers. So in this case, this producer ID 3, for example, all of its, I don't know if you can see it very well, but the intentions for those first 4 records are, they're basically going to get removed. So we're removing all of the state that corresponded to that producer ID 3. And what we do in Kafka is we maintain this invariant that basically the log is the source of truth for all of this state. And we update the producer state cache always to reflect that. So what happens is when you have like a big deletion from the tail of the log, then that producer state is gone. And that's where we get that unknown producer ID coming from. So when we were writing this, of course, we thought, people should be, producers should be active, they should be doing stuff. But it turns out that there's another case that I think this was coming out at about the same time that EOS was coming out. Basically, like we have a mechanism in Kafka where if you've finished reading some data, you can delete it. So Kafka Streams uses this for so-called repartition topics. I won't try to explain repartition topics because I don't understand them. But basically, it's used for rekeying the data. And but the point is, once the consumer has kind of finished reading this data, the data isn't needed anymore. So it's already been pushed to these output topics. So what Kafka Streams would do is actually like delete all of the log. So basically, in this case, when we had this happen, you're losing all of the producer state. So it becomes from just like a rare case, which people should never hit, to actually a common case. And so basically, like what you actually get is something like this, and that's really what caused all these unknown producer ID errors. So how do we fix this? I think there's kind of like 2 things that we need to do. So first one, as we're writing to the log, we're maintaining the state. The state has to be like rebuilt from somewhere. We said the log is the source of truth. So it has to be rebuilt from somewhere, like after a failure or something like this. So we keep snapshot files to help us rebuild that state. So we can go back to like what's the latest snapshot file, reload that state, and then the amount of that we have to read from the log is small. And so basically, we're taking these snapshots periodically. So the basic idea, this is pretty simple. When we remove the data, we remove the snapshot, and like as we do now, we're getting rid of that producer ID. So yeah, maybe we just don't do that. So basically, rather than getting rid of the state, even though we lost it from the log, there's really no harm in maintaining it in the snapshot. So basically, even though we lost the records for that one, we can keep it. So I'm gonna go ahead and skip through some of this. I think the main thing I want to say about this is just that this is probably like the 95% of the solution. But it can still happen because the log is no longer really 100% the source of truth anymore. That's if you're doing like a partition reassignment, for example, the new broker that's coming up as a replica, it won't have all of the state, this soft state that's not actually present in the log. So there basically is still some cases where you can get a unknown producer, even though even though we have this improvement. So the other part of this is really about yeah. In fact, I'm just going to kind of skip through this if you don't mind. I think that the main thing is really that we are. Once we reach a state where basically we got this unknown producer ID, currently today we would just fail and say that, okay, that's it, producer, the producer's done, like you need to close it down and start up a new one. Instead, what we have in KIP 360 is basically a way to get ourselves out of that state. So for example, if we were in the middle of a transaction, it should be possible, it should be safe to abort whatever transaction we were in and then start a new one. And so basically then we can start off from a clean slate again. So that's kind of the approach there. So really the summary here is that current impact when you get into any kind of error where maybe there was an out of sequence error because of a bug or something like this, or an unknown producer idea, which is like just a different class of the same problem. We have a way to get ourselves out of that state. So this is what I mean about the resiliency in the producer. So we can always abort our transaction, bump our epoch, and resume. Okay, so then I'm going to have Boyan come in and talk about the second part of EOS that we've thought about improving, and this is producer scalability.
Thank you, Jason. Yeah, let's get to transition part 2 for now. So my work recently is actually on the improving for the scalability for the client. So as Jason talked about, that usually you actually have like a consumer group working all together, take some input data, put to output. So this is actually what Kafka Stream is actually doing. So Kafka Stream is just like a very lightweight Java library. So it leverages consumer and producers to do the network traffic. So basically we have the notion of the stream thread. Every stream thread is just like the processor we just mentioned. So they are isolated, they don't talk to each other. And then, so if you zoom into one of the thread, it's actually further split the input data based on the partitions. And we have this notion of stream task, which is just mapping from the input partition to the task. For example, if you have like a topic with 3 partitions, then you do aggregation job on top of that, you get 3 tasks. But that doesn't mean every partition mapped to only one task or the other way around. So because you can join 2 topics, then that means one task can be mapping to 2 partitions. So that's the thing you want to know. But basically, the task definition is kind of like strictly mapping towards our input partitions. So you can think all the task identity are unique. And then we only have 1 producers and consumer for the normal processing. We haven't talked about the exactly ones, but when we turn it on, then the single write scope for the transactional ID semantic, how do we guarantee that? If we just use this model, there's got to be a problem because I think Jason already talked about this, and I will just go through really quick because we have rebalance. Consumer can shuffle your assignment across the entire group. And then when we add a T1, the old tasks, they're having some ongoing transaction, possibly if someone has a unclean shutdown. Then when you're trying to start your job, you don't know like whether those tasks 0 to 5, are they have any ongoing transactions unfinished, or you can proceed. Because the old, the way that the single writer is guaranteeing is that just you need to make sure that you can always bump. So in this way, if you can dynamically assign the partitions, so that no longer works. So you always need to make sure that you have some tracking of the transaction state across generation to make sure that you can always start from a clean stage. So I think I just talked about the problem we are solving. is basically, I think if you work with consumer before, consumer always has this dynamic assignment semantic, while contrary to that, producer does not have any notion of the a group. So you never heard of like a producer group or something. So basically, this is a semantic mismatch between the two, and we have to find a way to fix that so that we can improve the scalability. Well, just this makes us wondering like how we solve the problem today. It's actually a pretty straightforward solution. We just split the producer. For every single task, we got a producer, so that you can use the task ID as the producer ID, because like I just mentioned, task is mapping exactly once to the partitions. So you can always make sure that within the same group, that all the task ID will be take position by someone else. And then every time you initialize a new producer, yeah, you just need to reinitialize the transaction, and then yeah, you will be in the clean state. So yeah, in this case, then all the dependencies are clearly tracked. So no matter where this task goes, you will get a new producer. So that means like this, for example, this task 2, someone else will take this task ID. Then I don't need to worry about like whether someone else is working on that, because once they reinitialize the transaction, it will actually be either commit or abort. Yeah, and then the epoch will be bumped. So it should be safe. So correctly is problem solved, but we haven't solved the scalability issue here. As this same diagram for producer, you always have like separate buffer pools maintaining memories, and you accumulate data for network transfer to enable like the produce to the broker. So one of the most important design for producers to batch the our requests to the broker. So if you separate all the producer instances for your input partitions, then there's no more batching, and you're trading off with more like IO threads, more sockets, connection to broker. So those are just the overhead of turning on the exactly once. So we always want to go back to the way we have, which is like for one stream thread, we should only use one producer, but currently we're trapped in this semantic problem. So to find the fix or the solution, we need to be pretty much clear of our goal here. So first one is, of course, you need to find the dependencies across generation. And then the other thing is you still can detect any zombie when you actually turn on this transactional producer group. Okay, so first, let's say when we initialize the transaction, every stream thread they will bump up a couple of task producers so that they can initialize. So we hash the transaction ID to find the correct transaction coordinator. So each of the thread can talk to different transaction coordinators. This is something distributed. So you don't have like a global view of your Kafka stream group, like how everyone is doing, what the assignment you get for each of these individual producers. But if you take a deeper look into the graph, we haven't talked about one important role here, which is just the position topic Jason talked about. It's actually the consumer offset. So there's another coordinator called group coordinator maintaining the state of the consumer group. And the discovery of the group coordinator is based on your hashing of the group ID. So all the threads will talk to the same group coordinator. And of course, group coordinator knows what partition assignments you are giving to each of the thread. So you actually have something centralized to track all the states, which makes this is a good place to do the dependency resolution. So the other thing is about the zombie case. I think we talked about using producer epoch to fence some of the out of sync client. But in this new model, if we have like producers per thread, it's no longer working that way, because, for example, in this case, we have some thread T1 start a transaction, and it will write to rewrite offset to this group coordinator, and then because this is the first time it writes, so you will accept it and remember the epoch for P1, and then somehow you rebalance this task, and then T2 starts another transaction session, and then it will write another offset. So this one also gonna be accepted because yeah, it's just a good PID and epoch we never seen it before. If somehow P1 goes back online, this time you have no guarantee that the transaction of that P1 has been aborted before, because no one used T1's transaction ID anymore. And if we are unluckily within the transaction timeout, you don't bump the epoch anyway. So this offset commit can give you dirty data into the consume offsets. So that's the tricky part of allowing like the assignments going in between the threads, because you don't have like a unique ID to help you to fence any of the last generation transactions. So after we know the problem, let's talk about the solution, which is currently ongoing in the community for Keep Forward 7. So first, based on our observation, we're going to use group coordinator to solve this initialization problem. And just going back to the graph where we talk about this awkward failure of in between one transaction. So in the single writer model, it actually is okay for you to maybe just going forward by ignoring all the pending offsets when we read the position topic. But in the new case here, it's no longer safe, right? Because if say we can continue from maybe input B, and then somehow this transaction on T1 hasn't finished, and it actually on the step, maybe for example, we already read all the data, but we just haven't read the transaction marker or something. But yeah, sorry. If we already read the transaction, the prepare commit message to the transaction log, you actually roll forward, and then all of this data can be committed in the next step. So you're actually reprocessing the data for B into twice for the prime B. So that's pretty bad. So instead of just proceed when we see pending offsets on the position topic, what we should do is we can just hold and wait there, so that we can wait for this T1 transaction to be wiped out by the transaction coordinator, because we always have a transaction timeout to help us get rid of this pending offsets. Because in the new model here, single writer mechanism doesn't help us defect this pending offset. So you no longer can make sure that this pending offset will be gone anyway. So you just take a conservative approach to back off until you reach the transaction timeout for T1. Then all the pending offsets will be cleared. You can safely proceed. So that's the fix to it. So yeah, sure, go ahead. Oh.
No, my
yeah.
No, my question is,
Sure.
How do you really clear the state if this is like a write-ahead log? You cannot really delete things there, right?
Oh, it's not the deleting. I think for all this pending records, you will eventually write a marker saying whether this is something success or fail. So it's actually just by pending forward of the markers, then this offset will no longer be something we call pending, but it's something like committed. So yeah. So it's not like we were actually deleting data from Kafka log. It's just you write another record saying whether this is.
And where is the marker persisted in this picture?
So the marker is right here on the position topic. So all the topics we have touched for either just general output topic or consumer offset topic, those are just, we produce some data, but we always mark them as pending. So when you're in the pending stage, if you configure your consumer as recommitted, you never see those pending messages. But until you write like a clear marker to those topics, then those data will be marked as committed or aborted, so that you will either skip them or just return them to the consumer. So okay. Cool. Thanks for the question. So let me get this really quick. So I think the solution is pretty clear with just a couple of observations with the consolidating of the group coordinator. You're basically relying on the transaction timeout for this time to help you abort the last generation transactions. But just, well, the thing we're discussing here is just worst case, because in normal cases, when you rebalance or you shut down, you can definitely write a end transaction request to the broker. It just sometimes you're not ending that not that gracefully. That requires you to be pretty much conservative in this way. So the other thing about the zombie, I think we have talked about this. We haven't talked about this notion on the consumer side, which is if you know a little bit about the group rebalance, there's a status marker called generation ID on the group coordinator. So it actually remembers the group state during every single rebalance we did successful. So if you use generation ID, you can actually fence out of sync consumers. And in this time, we realized that we can still use this notion, so that we basically just we use the generation ID in the time we commit the offsets, so that if you say, oh, this is generation 2, it matches what I have on record, so this is a good client, then you can always proceed. When you rebalance, the new thread, the new client T2, it will know the same new generation ID 3. It will still make good progress. But for the zombie, T1 is out of the game, so you basically won't be able to make a dirty commit because your generation ID is out of sync. So yeah, this is just the fencing. So you no longer use the epoch because the single writer schema is not guaranteed, but you can use the consumer group generation ID in this case. So by all this works we are doing here, eventually we want to reach the stage that we can bring back single producer per thread model to Kafka Stream, so that you can turn on exactly once by default. So that's the ultimate goal. So just a recap of everything we have talked about. You always start from initial transaction. And in the new model here, you be conservative when you fetch the offset by waiting until the abortion of the pending transactions. And then you will fetch data from input topic, you do some work and then produce them to the output topic. Then this is the time you need to make sure you know the offsets you're gonna write. So you basically talk to the transaction coordinator to remember the offset topics you have written. And then you will talk to the group coordinator to commit offset. And when you're committing, you need to use generation ID to make sure you're safe to go. You're not a zombie. And then once those steps have done, and then you will just call commit the transaction, and then transaction coordinator will write a marker message in local, and then it will try to write the success marker to all the touched partitions. Oh, sorry. Yeah, sorry. Actually, maybe it's not input topic, but okay. So last thing, once you have done writing the transaction success markers to all the touched topics, you will just finish the transaction. So just summary what we have talked today. So I think, yeah, basically this EOS model we developed 2 years ago is pretty elegant. But the thing is, we still are having some gaps to reach the maturity, and we are currently working on them. Hopefully, eventually we can bring Kafka Stream to a more scalable state, and then we can enable exactly once, yeah, by default. Okay.
Questions?
I have a question on those transaction coordinator and transaction log.
Yes.
So where do those kind of, is transaction log another Kafka topic?
Yes. Yeah.
So is that like each normal topic has one transaction log topic, or like does each topic partition has one transaction log?
Oh, the transaction log is actually based on like your discovery of the transaction coordinator, right? So it basically just you hash your transaction ID, and then all the transaction ongoing with this transaction ID, those markers, those log messages will be written to this partition. So who is the leader of the transaction log partition? Yeah, it's the.
So just to add to what Boyan said, it's actually the transaction topic is a very, very simple. Well, it's similar to the offset topic that we have for group coordinator. You predefine the number of partitions for your transaction offset. Sorry, for your transaction topic, and then all the producers with the same transactional ID will always talk to the same coordinator, hence writing to the same transactional log. But based on the number of partitions you have, more than one transaction IDs may actually talk to the same coordinator and write to the same transaction log.
So if you have multiple input topics, can they go to the same transaction log? Or?
The granularity is based on the transactional ID. So if your transactional ID, say transaction ID A, is actually writing for multiple partitions, it will all go to the same transactional log.
Okay.
Yeah. Okay.
One more question.
Thank you. So in all these presentation, you talked about basically dynamic partition assigning. Does it change on manual partition assignment at all? Like.
Oh, no. I mean, yeah, that's a good question. Actually, consumer has two modes. I think most of you know, like subscription or assign. So basically, in the standalone mode, the current model definitely works. So I think the thing I talk about, the scalability, is only on the. Yeah. So yeah, they're totally different. So my case, it only applies to the subscription type. Yeah.
Okay. Thank you, Boyan. And in case if you have more questions about the details of CAPE 360 and 447, we have actually pretty well-written documentations on the Confluence page of Kafka improvement proposals, or AKA KIPs. So you can just go to the wiki pages of 360 and 447 for more details about how we actually want to improve on that. And hopefully we will get both of those features into the next release, which is 2.4 in end of September, let's say. Okay.